Welcome back to the lab, folks. So we're going to wrap up our review of the DPOS350P from FNIRSI today. But before I go on to the frequency response analyzer or the spectrum analyzer, I want to show you a couple of things. One thing I didn't show you that I'd like to show you, and something I did in the last video that I did incorrectly, so we're going to do that properly at this point. First thing I want to show you, okay, we got this little 10 megahertz square wave going into it. And it's not a perfect square wave. You can see some rounded edges on it. And what that'll tend to do, like a perfect square wave, is going to just have odd harmonics. But if you see that kind of rounding on it, you're going to get some even harmonics in there as well. And I guess that's what I'm going to show you will help you do. It doesn't really do any measurements or anything. So if you go to the channel menu here and you see a FFT display, you can switch that on. And there we get this kind of a little FFT display. Now if we take a few more samples here, we can see how this spreads out a little bit, and you can see your odd harmonics coming down here like this, and then but you can also see your even harmonics in there. I guess it's good for that, but you can't do any measurements with it. You're not given a frequency scale or a dB scale or any kind of linear scale, nothing. So I don't know if that's going to be useful to anybody or not. It might be for a quick view, just like we did here. Okay, now I need to set up a little bit differently for the next thing. So what I did the last time, what I tried to show was both channels running off the same signal. But I had intended to do something else, and then I changed my mind before I actually did the presentation, and I upped the frequency way beyond what it should have been, and it wasn't set up properly for that. So what I'm going to do now is I'm going to attach this to a different generator here. I have on here what's called a resistive splitter up by the generator. It's not something I'm proud of, it's just something I threw together myself, but it should be okay for what we're doing here. So it comes down here through these two separate lines here, exactly the same length each, into terminators here. So let me zoom out, you can see that a little bit better. These two lines coming down into these two pass-through terminators. So we're going to get exactly the same signal, and it's not going to be delayed by the length of one of these cables as it was before. Let's get rid of this FFT thing here. Turn on channel 2, get them on the same scale here. So let's actually just bring them all into the middle here, and we can see this almost perfect alignment here at 10 megahertz. Let's bring them both up a little bit. So I have this set up that we have exactly 100 millivolts, and you can see there's just this very slight difference of 0.5 millivolts between 1 and 2. Personally, I think that's very acceptable on a scope like this. No problem with that at all. Let's go up to 50 megahertz here. And bring this out again. So now we do see that there is a little bit of skew here. So, but if we look at the levels, they're pretty good. So it's come down a little bit here by 2 millivolts, and it's still within a half a millivolt over here. Now let's bring it up to 100 megahertz, see what happens there. We're back to 100 millivolts. Oh. And within a half a millivolt again. Let's go 125. We're rolling off just a little bit. 150. Okay, we're peaking again. We're about 5% high, and on the second channel 7% high. That's a very, very small percentage. So we haven't varied by more than 0.3 decibels over the entire thing that we've looked at here. Personally, I'm okay with that. It would be better if it wasn't there, but it's there and it's quite acceptable. See, we'll do 175 megahertz, which is more than what's rated for. Yeah, we're still fine. So bandwidth is at 150 megahertz here, so we're at 175 megahertz. It's behaving just fine. But now we have an opportunity to try and put maybe a cursor on these and see how far these really are apart. Okay, so it looks like we're actually at around about 685 picoseconds, or 1/10 of what I showed before. So this is a more accurate assessment of the skew. It'd be nice if you could deskew it, but there's no control as far as I know to deskew it. But that's not nearly as bad as what we had seen before. So that's on me. That's my fault because I didn't set it up properly. Now, just to make sure that this is not the fault of the generator here, let's change these inputs. No, it's actually exactly the same. So it's exactly the same position and everything else, and the voltages are the same too. So, okay, so that is in the scope. All right, guys, let me set up now to do the frequency response analyzer, and we'll come right back. Okay, let me show you what we got here. So we've got the generator output coming directly into this T here, going into channel 1, and coming out of that I got some alligator clips. These will be connected to the input of the filters we're checking, and then this cable here coming out of the output of the filters into channel 2, and that's, I think, one of the best ways you can hook it up. But first of all, we want to get in. Let's get into here, into frequency response analyzer. Okay, it's just measuring nothing there. Let's connect these up together to get a baseline. We'll do a calibration on it. So that'll take any contribution from all the cabling here out of the equation. Not that it's going to make much of a difference, because we're at audio frequencies here, so it's not a big deal. So we're going to calibration, confirm that they're all connected together. They are, and then go ahead and do the calibration. And it's now done. So let's hook it up. This first filter here, this is a low pass filter. Now if I go from here to here, I should get a band pass filter. From here to here is a high pass filter, and from here to here is a band stop filter, or band attenuate filter. So just let's have a quick look at those filters and see what it makes of them. Alright, let's zoom back in here and have a look at this process. Yeah, this is a low pass filter here. That's pretty well okay. What they don't do here, for FNIRSI are not putting any averaging into it. Like if I do this on multiple other scopes, what they do is when they do a Bode plot, or each of the frequencies, they'll measure the voltage and the angle and average them over maybe 10 or 15. This one just goes once, as far as I can see, because it's very quick. So you're going to get some deviation, and then the next time you run it, it's not going to be exactly the same. It should be similar, but see, it's not exactly, because it didn't get that little bump in there. So this is what that's supposed to look like. This filter is set to be down 3 dB at about 1 kilohertz, and I've tested this filter before, and this is pretty much right on. So let's now go to the high pass filter, and we'll take a shot of the high pass filter. Yeah, that's really nice too. Now again, you see all that waviness there in the phase. Just try to smooth it out in your own mind, because if they did do some averaging on it, that wouldn't be that bad at all. It'd be perfect. All right, let's look at the band pass filter. That's what I needed to see as well. So yeah, that's exactly what I recall it being like before, except for this little waviness at the end here, which again I blame on not having any averaging. So like you can go and put it into loop mode, and it'll keep doing these, and then you can see the kind of variation you get. And this is the kind of stuff that should be averaged out by doing maybe 5, 10, or 15. It would take a lot longer to do 5, 10, or 15 samples at each frequency. But if you want a clean plot, you put up with it. On my Siglent SDS 1104, it takes a long time to do one of these plots. Like you can go put on a coffee, sit down, watch a little bit of TV, and then come back, and it'll finish the plot. But that's perfectly okay. From my perspective, to do some engineering on a circuit that I'm designing or something like that, I don't mind that. I want to get the proper results. They could really improve it by A, giving us a lower frequency on the big start, and B, by doing some averaging. Give us the choice. Let me be able to put in 1 or 5 or 10. So this is the band stop, band attenuate. Now if I recall correctly, this one was supposed to be about 20 dB down in the middle. Well, it is about 20 dB down in the middle, but I don't remember all these extra poles in there. In fact, I'll put up a shot of what this filter is supposed to look like. So yeah, you can see that there's a little bit of an issue here. Let's put it onto loop and run it and see what it looks like. This pole here seems to not go away, and I don't know what's causing that, but everything else would get averaged out, I think. And of course you can use cursors, so that's minus 2 dB there, and we go over here to minus 3 dB from that's 5 dB down. Oh, around about there. And then we do the same here, about 5 dB down. There we go. So we can see that our band is it's a 3.3 kilohertz band between 391 hertz and 3.69 kilohertz. So you can actually use this for decent measurements. And then of course if you wanted to get what your center frequency is, you bring it in here to the absolute peak, and then that'll give you your center frequency of 1.29 kilohertz. I think it's a really decent little frequency response analyzer or Bode plotter. If it had the averaging, it would be phenomenal. Alright, let me set up now to show you the spectrum analyzer, and that should wrap things up. Alright folks, here is the spectrum analyzer. So I've got a 10 megahertz signal going into it. Let's set the start frequency at something reasonable here. Let's set it at 8 megahertz. And let's set the stop frequency, we'll set that at 12 megahertz. Just to get our center point in there. And let's go up here. It says function, and it talks here about FFT length. I don't think that's FFT length. Yeah, I think what they're really referring to is the resolution bandwidth. This is our maximum here. As we come down on that, the number of samples goes up, but the resolution really gets gummed up. So it's not really good for analysis in close to the fundamental, at least not at this frequency range. Might get things a little bit further up, but let's broaden our sweep here, and we put a start frequency in of 1 megahertz and stop frequency of 19 megahertz. I would put the reference here at 70 dB. That attenuation looks pretty good, and all you really have now is cursors to measure with. Let's see, that's 61 dB millivolt. Yeah, so now if you want to look at a harmonic series, we probably have put in a start frequency of more like let's say 5 megahertz and a stop frequency of more like 200 megahertz. Now this is the same signal, exactly the same signal we were looking at before when I showed you the little FFT that you can bring up on your channel. And we can see, yeah, we have all the odd harmonics where they should be, and they're looking like what they should. But then you can see all those even harmonics in there as well. So that tells you right away that your square wave is not really a fantastic square wave. And we're on slow move. Let's do a fast move over to neighborhood. And then we'll do a slow move until we can get C1 here at a peak. So look at the dB scale here and try to get it peaked. Right there. So now we know we're on the frequency, and it's saying 10 megahertz. And then if we want to measure how much, and we can bring this cursor over. Okay, so we can see it is 18.7 dB down from the fundamental. Now it has some doodads thrown in here. You got your 3D display. They also have, let's turn 3D off, but they also have a waterfall display, which, you know, similar to the 3D display, gives you that same kind of imaging, whichever you like best. And you can actually, for what it's worth, you could put both of them on at the same time. Now let's put this down to 4K and see what happens. So things move a lot faster, it gets a little bit grainier, but it gives you your information a lot quicker. If you're looking over this range from 5 megahertz to 200 megahertz, this is probably better than looking at it in more detail for, you know, for looking at these displays here, the 3D and the waterfall. Alright folks, let's see, what do I think of this little oscilloscope? I'll put the price up on the screen, I've forgotten off the top of my head. Yeah, you can't get much in that range that I think really beats this. I mean, I've been on EV blog and I've browsed through a couple of the threads about it, and some people got different results than me, but I don't know if you can always blame the scope for those results, because you saw what I did in the last video. I did something silly and I got really bad results because of it. And then when I did it properly, the results improved dramatically. You gotta take some of these things that you see in these reviews on the internet with a grain of salt or two. As for me, what do I think of the scope? I think it's a decent little scope for that kind of money. Honestly, I do. Yes, some of the features in it are a little bit disappointing, The fact that in my case, that it peaks both when we did the bandwidth sweep and when we looked at it just today, where we were looking at two channels together, again doing the bandwidth sweep, it was within 7% or 0.3 dB, all the way until it falls off to the 3 dB points. How can you fault that? If you're not out there trying to build the latest cruise missile or stuff like that, I think you could probably live with a 0.3 dB flatness across your scope's range. So it will do 350 megahertz. It doesn't unfortunately have points or vectors. It's only got sin x over x. On the good side, it's really well made. Like, it's so solidly built. It's a little bit noisy. The fan's a little bit noisy. Spectrum analyzer is useful, if not something we call a spectrum analyzer, if you're getting what I'm saying. Calling it a spectrum analyzer sets in your mind certain capabilities which this doesn't have. The frequency response analyzer, fantastic again, but there's always a but. They should have allowed for the user to enter in a number of averages for each frequency so that you can get a better idea of what the exact response is. The generator, I like the generator. The generator is really good. Within its capabilities, it does very well. And the fact that you can do a capture of any waveform you want on the screen here, and then use that, put it into the generator, use that up to 3 megahertz, that's really great. I think it's a good little scope. I think it's worth the money. I think there are some little quirks to it, but I don't think they're that bad. All right, folks, that's what I think of the FNIRSI DPOS350P. I appreciate you guys coming out to watch. So we'll see you in the next video. Bye-bye.